Gene yani content olarak, başlıklar olarak aynı derse dönüşüyor ama içerik ve derinlik olarak biraz daha farklı olacaktır. Orada ben koordinatör olarak kendimi paralamak durumunda kalıyorum. Hocalarımızın sorularını. Keşke burada da mı yapsam acaba? Burada pek yapmıyorum ama. Şey nasıl geçti? Midterm 2 nasıl geçti? Midterm 1'de de böyleydi. Bu da hani siz mesela sizin nasıl geçti?
Hocam birden daha iyi geçti.
Birden daha iyi. Güzel. Yani zaten birazcık şey olsun, yani bir de düşük çıktı bence curve. Dolayısıyla birazcık yükselsin diye açıkçası biraz fazla şey yaptık. Efor sarf ettim. Finalle ilgili bir isteğiniz var mı? Olmamasını istediğiniz
hocam,
bir şey.
Hocam şu uyarısını koyulan sonra sizin sorunuz mu?
Yok, benim değil. Afşar Hoca'nın sorusu. En son soru benim sorumdu. Yani bode sorusunu ben sordum. Onun sorumlusu benim.
Yani mesela şu modeli yapıyoruz ya, hani böyle bir şey yapacaksak da çok detaylı bir şey olması olabilir.
Yani o derece şey yapamam. Yani şekil şeylerini yapabilirim. İşte sorularla ilgili istekler olabilir ama o derece hocalara şey yapamıyorum. O derece direkt aman şu soruda da şu şey olsun. Hoca soruyu getirdiği zaman böyle bir feedback verebiliyorum. Keşke şunu da şöyle yapsak iyi olur filan gibi. Ama böyle istekleriniz varsa şu anda söylemek için son şansınız. Bugün final toplantısı yapıldı. Ancak evet buyurun.
Hocam bode çıkacaksa
Büyük bir bode istiyorsunuz. Peki. Tamam okey. Başka?
Hocam her hoca kaç soru soracak bilmiyorum da yani 3,5 saat böyle bir sınav.
5 hocayız, 5 soru soruyoruz.
Hocam 5 soru süre ne peki?
Şu anda bilmiyorum. Başka isteği var olan? Midterm'le ilgili yorumu olan, feedback'i olan. Efendim? Midterm finale kadar çok zor okunması gözüküyor. Dolayısıyla itiraz saatleri finalden sonra yapılacak. Hem midterm için hem de final için muhtemelen. Yetişmeyecek yani.
Hocam peki bayramdan sonra yapalım.
Bayramdan önce notları verme planımız var. Dolayısıyla finallerin son haftasında ve make-up'ların olduğu hafta muhtemelen kağıt gösterimleriyle ders tamamen biter ve harf notlarını veririz. Bayramdan sonra kalmamayı planlıyoruz. Başka? Buyurun. Efendim? Anladım. Olabilir. Bilmiyorum artık. Bu dersin ana konuları say diye saysanız mecburen naykuşlu sayıyorum. Dolayısıyla öyle işte soru gelmez falan gibi bir şey diyemem maalesef. Yani çok sevilmediğinin farkındayım ama bir içerik oluşunca mecburen. Başka?
Hocam.
Buyurun.
İlk konularda hani bakmamız gerekiyor ya.
Hı.
Bir sorduğunuz soru tiplerinden farklılarsak mantıklı olur mu yoksa hani?
Yok, herhangi bir assumption yapmayın. Aynı şekilde sorular gelebilir. Yani aynı content'te sorular gelebilir. Buyurun.
Hocam modelingden ağır bir soru beklemeli miyiz ne?
Neyden?
Modelingden. O ilk physical.
No comment.
Hocam puan dağılımı belli olur mu? Hani midterm 1 içeriği, 2 içeriği veya final içeriği.
Yani genellikle biz bütün soruları eşit ağırlıklı yapmaya çalışıyoruz. Çok nadiren hocalardan istek geliyor bana. Yani şunun puanını biraz yükseltsek iyi olur zorluğuna göre falan. Dolayısıyla mesela işte birinci midterm kolay görünen bir soru gayet yüksek puanlı olabilir veya zor görünen bir soru düşük puanlı olabilir. Genellikle sorular eşit dağıtılıyor çok nadirdir yani bana birisinin istediği. Sınav dosyasını ben hazırlıyorum. Nadirdir yani birisinin puanı değiştirelim falan dediği. Buyurun.
Hocam yine en azından bir veya iki soruyu independent farkları olacak şekilde yapsanız.
Bunu söylüyorum. Bunun için özel bir uğraşımız var. Yani hocalar soru getirdiğinde de benzer şeylerim oluyor. Yani söylemeye çalışıyorum en azından. Yani ilk kısmı yapamayınca tamamı gitmesin falan diye bir çalışma yapıyoruz final sorularını hazırlarken. Böyle bir şey. Yani gene tamamıyla garanti edemem. Her birisinin independent olmasını falan garanti edemiyorum ama en azından ilk şıkları yapamayanlara dair bir düşüncemiz var. Evet öyle bir şey. Buyurun.
Hocam soruyu bilmiyorum ama soru bol şeklinde soru var mı?
No comment. İçerik hakkında şey söyleyemem. Okay. So we are in the state space design part of the course, the last part of the course. We have two concepts: controllability, observability, and we have something called state feedback. We're going to see that state feedback is actually much more powerful than the output feedback that we have seen so far in the course. But the first thing that we are going to see is going to be something called controllability. It's going to be a property of a state space representation of a system. And it's going to be an important property at the end. When we apply something called state feedback, we are going to see that controllability is going to give some power to state space feedback. So let us write controllability. I will start with its definition. A linear time invariant system in state space form is said to be controllable. Or sometimes people say completely controllable. This is the same thing. If and only if, this is definition, it's possible to transfer the state vector from any initial state x0 to any final state xt in a finite time interval by using a suitable input u of t. So this is the definition of the meaning of controllability. So we have a state space for a system, okay? So let us say that our state has two dimensions. Then state space is x1 and x2. This is R2, which is our state space. And we know that we have the equation for the system x star is equal to ax plus bu. So the system response depends on two things: initial condition and the input. Okay. So here controllability is the following. Suppose that I give you any initial condition. Okay, this is my x0 initial state for the system. By choosing an input u of t, a suitable u of t, can you make the state come to any final state? This is my final state, x of t. Okay? Can you make the state by using this equation come to any final state that you like by using a suitable input function? If you can do this, then your system is controllable, or your state space representation is controllable. If there are some initial and final state pairs for which you cannot do this by choosing any input, then the system is called not controllable or not completely controllable. So controllability is the ability of the input to steer the state from any initial condition to any final condition. So maybe the best thing that we can do here is to see some examples before understanding completely what controllability is. Let us say that our state equation is given in the following form. So I have 1, 0, u, and y is equal to cx. Okay. So here, that is the A matrix. This is A, B, and C. If I tell you that controllability is only dependent on two of these quantities, two of A, B, C, which two would you select as related to the controllability? The output does not appear in that definition. We don't really have anything related to the output in that definition. It's only related to the input and the state behavior. Okay? Controllability is only related to input and state behavior. So which two would determine controllability of this system? Only A and B. Okay, that is going to be a remark here. Controllability is only related to A and B and not on C. So C is irrelevant for controllability. Okay? So now let us try to look at the equation. So only this A and B, only the state equation is important for controllability. For observability, I will have only A and C. Okay? So in that case, B will be irrelevant for observability. We are going to see what that is. So here I will write what the system equations are. I have x1 dot is equal to minus x1 plus u, and x2 dot, these are the state vector elements, and I'm writing individual state equations here. Okay? x2 dot is equal to minus 2 x2, and u doesn't appear in the equations. Okay? So we say that the second equation is independent of the input. Okay? And the first equation only depends on the input of the system. So when the second equation is not dependent on the input, I can actually solve this differential equation quite easily. What is x2 of t? What is the solution of this differential equation? x2 of t is e to the minus 2t times x2 0. Okay? So that is the solution of the second differential equation. So we say that x2 of t, whichever input I choose for the system, x2 of t starts from an initial condition, that is x2 of 0, and it decays with the time constant 1/2 seconds. Okay? So input does not change this behavior at all. So now the question is this system controllable or not? So, for example, if I give you some initial condition, this is x0, and if I give you an arbitrary final condition, this is x of t, can you find me an input function, u, which would steer the state, according to this differential equation, which would steer the state from x0 to x final in finite time? That is the question. Or, if the system is not controllable, I will be able to find some initial and final state pairs for which, whatever input I choose, I will not be able to steer the state from that initial condition to that final condition. Okay? Can you find such state pairs to me, for example? So let me say that the initial state is 1, 1. Okay? Tell me one final state for which, whatever input I choose, I will not bring the state to that final state from this initial state.
1,
1, 10. Okay? Why is this impossible? Because I see that the second state is always decaying. Whatever input I choose, the second state should always decay. Even if I can change the first state using the input, I can actually keep it constant by actually cancelling this effect here. But the second state should always decrease for this system in magnitude. So we see that for this final condition, the second state should get larger. So this is really not possible for this system. That means that this system is not controllable, or it's not completely controllable. Okay? So by seeing only this example, you might actually think that controllability is related to 0 elements inside the B vector. It's not actually like that. Unfortunately, it's not that simple. Sometimes B vector can be filled with all non-zero elements, and the system might still be uncontrollable. That is going to be our second example. Let us see how such system can be uncontrollable. Let us say that this is our A, B is 1, 1, and Y is equal to, and I really do not have to write the output equation. Okay? So now let us try to investigate if such a system is controllable or not. I will again write the individual equations. x1 dot is equal to minus x1 plus u. x2 dot is equal to minus x2 plus u. Okay? I have these equations for this system. And now the question is again, is this system controllable or not? Can I steer the state by using the input from any initial condition to any final condition? Or are there initial and final state pairs for which I cannot do this for any input function? Suppose that I choose the initial condition x0 to be 1, 1 again. Okay? Tell me a final state value for which I will not be able to steer the state by using any input function. So here, the interesting thing is that states would satisfy the same differential equation. States would have the same input, okay? The same input enters into both states, okay? And the differential equation coefficients for the two states are the same as well, okay? Solution of a differential equation is dependent on the initial condition and the input. And the inputs are the same for these two differential equations. Okay? If the initial conditions are the same, then the whole solutions should be the same for these two differential equations. Okay? Then here, if I take the state like this, for example, or let me say 2 and 3, okay? Can I bring the state from this initial condition to this final condition by using any input? In this case, it's not going to be possible. Initial conditions are the same, inputs are the same for two states, and as a result, the solutions of these two differential equations should be the same. That means that I will never be able to bring such an initial condition to this final condition in which the components of the states are different from each other. By using any input, I will not be able to do that. That means that for this system, again, there exists initial and final state pairs for which I will not be able to achieve the control task. That means that such a system is not controllable either. Okay? So in general, actually we do not check controllability in this manner. We do not write the individual equations and then we try to reason whether the system is controllable or not. In general, we use a check for that, which we will not be able to prove, unfortunately. But in general, we have a test for determining the controllability in an easy way. Okay? So let us write it as a theorem. The LTI system, x dot is equal to ax plus bu, y is equal to cx, is controllable if and only if determinant of a matrix that is called Q is not equal to 0, where Q is the following matrix: B, AB, A square B, going until A to the n minus 1B. Here n is the order of the system. This is the dimension of the state. Dimension of the state. Okay? Where this matrix is called controllability matrix. Okay. So here we have this simple check for controllability. Okay? So in order to be able to check controllability, we use only A and B, and we first form a matrix that is called controllability matrix. The first column of the matrix is the B vector, and the second column is A times B vector. The third column is A square B, and we continue until the power, which is one less than the dimension of the state, and then we end up with the last column, A to the n minus 1 times B. Okay? And then we look at the determinant of this matrix. If it is non-zero, the system is controllable. If it is 0, the system is not controllable. Okay? So now if I apply this theory to this system, for example, for the first example, Q is going to be dimension of the state is 2. That means that the powers here are going to increase until 2 minus 1, A to the 1. Okay, so this is going to be my controllability matrix for such a system. Okay, and here B is 1, 0, And AB here is going to be this matrix times 1, 0. It's going to be the first column minus 1, 0. Okay? So then I will look at the determinant of Q in this case, and it's going to be 0, which means that the system is not controllable. Okay? If you do the same thing to this system, it is going to be really, really simple. B is 1, 1. And A times B is going to be the summation of the columns. When you multiply a matrix with such a vector, you sum the columns here. Minus 1, minus 1. Determinant of Q is still 0, which is not controllable. So, by using this theory, I can give you an example of a controllable system quite easily here. Okay? I can just change the following. Okay? I can make this, for example, 1. Okay? When you look at such a system, then if I look at Q, it is going to be 1, 0. I have this thing. And then I can write A times B, which is the first column, minus 1, 1. If I look at determinant of Q, it is going to be 1, which is non-zero, meaning that the system is controllable. How can such a system be controllable? If I write the equations here, I would see the following. x1 dot is equal to minus x1 plus u. x2 dot is equal to x1 minus 2x2. Okay? So these are the system equations. So we see that the input doesn't enter into the second equation either for this system. Okay? Then how can I control the state? We see that the input controls x1. Okay? By controlling x1, x1 enters into the second equation. Okay? So we can control this x2 indirectly by controlling x1. Okay? So here you can directly change x1, and by changing x1 we can change x2 here in this system. Okay? So that is how the controllability can be achieved by using this new system. Yes.
Buradaki final value steady state olmak zorunda değil, değil mi? Yani herhangi bir t zamanında denk geliyor.
Yes. Yes, exactly. So here, remember, we have actually learned some state space representation that is called controllable canonical form. Okay? So a system in controllable canonical form is always actually controllable. That is why we give the name controllable to that state space representation. So let us write a remark. A linear time invariant system, x dot is equal to ax plus bu, y is equal to cx, where a and b are in controllable canonical form, is always controllable. Okay. Let us directly look at an example. Let us say that g of s is s plus 1 divided by s cubed plus 5s squared plus s plus 10. This is my transfer function, okay? And from this I will come up with the controllable canonical form state space representation. So we have actually learned this in the last lecture. And remember, the transfer function in that case was in the following general form. b1 s to the n minus 1 going until bn. And I have s to the n plus a1 s to the n minus 1 going until an. For such a general transfer function, controllable canonical form state space representation was given like this. bu and y is equal to cx. So here, for controllable canonical form, B vector is composed of all zeros except for a 1 at the end. Okay? So that is the B vector. And A matrix is filled with the elements minus A1, minus A2, going until minus AN here. The main diagonal is 0 except for the last element here. And the first super diagonal is composed of 1s, and I will have zeros everywhere else. Okay? And finally, the C vector is formed out of the numerator coefficients here, B1, B2 in reverse order. Okay, I have B. So now let us try to write the controllable canonical form state space representation for such a system. What should be the size of my state? What is the order of this system? Third order. So the size of the state is 3. So that means that I have a 3 by 3 matrix here, and I have U, and Y is equal to Cx. The B vector is the easiest for the controllable canonical form. It is all zeros except for a 1 at the end. And the C vector is composed of the numerator coefficients, and A matrix is composed of the denominator coefficients. The last row of the A matrix is going to be -5, -1, and -10. I have written these by multiplying them with -1. Okay. And then the main diagonal is 0 except for the last element, and the first super diagonal is 1, and I have the A matrix. And finally, I have the C vector here. What should be these elements? What is the C vector? I should start with this thing is 0 times s squared plus 1 times s plus 1. Okay? That means that I'm going to write here a 0 and then 1, 1. Okay? So that is my controllable canonical form state space representation. And now what I can do is that I can actually check controllability for such a state space representation. In this case, I will calculate my Q matrix. The first column is B, and then I will have AB, and am I going to continue? The order n is 3 in this case. That means that I'm going to continue until the second power of a. Okay? So I have a squared b, and that is going to be all actually. Okay? So now if I fill in this thing, b is 0, 0, 1. If you multiply this matrix with 0, 0, 1, what do you get? It's last row you get, okay? So here, when I multiply this matrix with this vector, I'm going to get the last row. The first column is going to be multiplied by 0. The second column will be multiplied by 0. And the third column is going to be multiplied by 1. Okay, so I have 0, 1, minus 5 here, okay? And then I will calculate a squared b, okay? Here there are two methods. The first method is calculate a squared and then take its last column, okay? If you want to spend time, why not? You can calculate a squared first, and then you can multiply it with this one. Otherwise, what can you do? Multiply this vector. This is AB, okay? This is already AB. If I multiply this thing once more by A, I'm going to get a squared b, okay? So when I just multiply this vector with that matrix, I will obtain a squared b. Okay? If I multiply this vector by this matrix from the left, I will multiply the first column by 0. The second column is 0, 1, minus 1, plus 5 times, minus 5 times the third column. Okay? 0, 1, minus 5. Okay? So the a squared b is just going to be this vector, as you see. So then it is going to be 1, and then 5 here, and minus 25, and plus 25 minus 1, it is 24. Okay? It is just this matrix. And actually, if you concentrate on this controllable canonical form, when you form this Q matrix, you would always end up with a matrix in the following form. There will be all ones here on the cross diagonal, and there will be some non-zero elements here, and there will be 0 elements always here. For the general controllable canonical form state space representation, you can obtain this Q, you can see that the Q matrix will always be in this form, okay? And let us calculate the determinant of such a matrix. Determinant of Q is equal to, I can calculate the determinant by using any row or any column, okay? So I will use the first row. It is advantageous for me to choose rows or columns with as many zeros as possible. So I choose here the first row, for example. It is going to be +1 times the determinant of this matrix. 0, 1, 1, -5. It is going to be -1. Which is non-zero, which is going to prove that this representation is actually completely controllable. But if you do the same thing for the general form, you would actually see that we would get such a Q matrix. And when you try to calculate the determinant of such a Q matrix, because of these ones here, the determinant will always going to be non-zero for such a Q matrix. Okay? And that actually means that if you have a state space representation in this form, it is always going to be completely controllable. Okay? That is why this type of representation is called controllable canonical form. So now we are ready for state feedback. And pole placement. So far in this course, we only applied output feedback ideas. So we had the following. In this case, k is a real number, okay? And I had the transfer function of the system, g of s, and we used this type of control topology in this course so far. So we have the input of this reference input, and I have u here. I have y here. What we did is that we fed the output back to the input side. Okay, we chose u as k times the reference input minus the output. This type of architecture is called an output feedback architecture. Okay. In these last lectures of this course, we are going to try to apply something called state feedback. In that case, k will no longer show a scalar anymore. It's going to show a vector actually, and we're going to see why that is the case. So I have the now state space representation of the system, okay, bu, y is equal to cx, and I have the output y of the system, input u of the system. Okay. Now instead of trying to feed the output only back, we can actually try to feed the whole state of the system back. Okay, but the state is a vector here in this case, and input of the system is a scalar. Okay, that means that before I can feed this vector quantity back to the input side, I need to convert it into a scalar. Okay, that is why here what we do is that we multiply this state vector with a gain vector that is also shown as k. Okay? This k here is now a vector composed of n coefficients, okay? N is the number of state variables. Then this becomes a horizontal vector, and state is a vertical vector. When I multiply them, I get a scalar again, okay? And then I feed this back to the input side. I have the reference input. I feed the resulting signal from this architecture to the input side. So the signal here is k1 times x1 plus k2 times x2 going until kn times xn. Okay? And then the input that I'm feeding back is u is equal to r minus I have k1 x1 going until kn xn. I'm feeding this whole state back to the input side. Okay? This type of architecture is called a state feedback architecture. We are going to see that this thing, if the state space representation has the controllability property, if it has the controllability property, we will see that this is really extremely powerful. Okay? So here, we know that in the output feedback structure, if you can actually, suppose that your open loop system has these 3 poles, okay? Suppose that this G of S has these 3 poles. These are the open loop poles. By changing this K value here, we can actually place the closed loop poles on anywhere on this root locus, okay? I can, for example, try to place one closed loop pole here, another closed loop pole here, and the third one here, okay? I will be constrained to this root locus by using that output feedback structure, okay? We will see that if this state space representation is controllable, we can act by choosing this feedback gain, state feedback gain vector, in some specific way. We will be able to place the closed loop poles for this system anywhere we like in the state, in the complex plane. So I can choose arbitrary locations. I want to place the closed loop poles here, here, and here. It would be impossible by using the output feedback structure like that, because these points are not on the root locus. But if the state space representation is controllable, I will be able to choose arbitrary closed loop pole locations that I would like, and then by choosing this K vector, I will be able to place the closed loop poles at those arbitrary locations. Okay? So controllability is therefore going to be fundamental in achieving state feedback. What is the disadvantage of this thing? Is there any disadvantage? This is nothing. K times X is nothing.
Complexity.
No. Yes. How do we measure the states? In general, you have position variables, velocity variables, acceleration variables in your state space, and you usually measure one of them, which we call as the output of the system. Okay. So here in output feedback, you only have to measure Y. All right. Measure the output, and sometimes you measure the input. Here you have to measure all of the state variables. Okay. Whatever variables they are. Sometimes this is going to be impossible. It might be, for example, a flux variable in electric air gap flux, for example, inside the electric motor. Then you have to break your motor and put some sensor inside, probably. Then sometimes this is impossible to measure the states, and sometimes it's going to be possible, but it's going to be costly. So extra measurement means extra sensor in your system. That's going to mean additional cost in your system. Okay. That is why actually sometimes in order to be able to apply feedback, we sometimes only measure only the input and the output of the system, and we give them to a computer. And in the computer, a differential equation solver calculates us an estimate of the state. Okay? This is called usually x hat. Okay? Not the actual state, but its estimate. So it is x dot is equal to ax plus bu, and y is equal to cx. We actually give this output and the input measurements to a computer, which is going to be a differential equation solver actually for us. And this thing might give us some estimate of the state, which is x hat. Not the actual state, but its estimate. And then we can try to feed this estimate back into the input side. Okay? In that case, I will get something like this. This computer, the algorithm that is run in the computer to calculate this estimate is actually called an observer. Observer concept actually complements the state feedback structure. And if you don't want to use additional sensors in your system, you can actually come up with some algorithm in the computer which can give you the estimate of the state, and that is called the observer. But we need a condition for successfully design an observer for a state space representation, and that condition is called observability. Okay.
So what was the input for that one?
Sorry.
What is the input for the last one?
Bu sistem hala input U'yu alıyor. Bu Y'yi output olarak veriyor. Observer dediğimiz sistem input olarak Sisteme verilen input'u da ölçmeniz gerekiyor. Output'u da ölçüyorsunuz. Sadece bu ikisini ölçerek state'in estimate'ini bazen hesaplamanız mümkün oluyor. Bu algoritmaya observer ismini veriyoruz. Ve de observer gerçekten çalışması için sistemin bir özelliğe sahip olması gerekiyor. Ona da observability diyoruz. Sistem bu özelliğe sahipse bu ilk seti gerçekten hesaplayabiliyoruz. Sadece input'u ve output'u ölçerek. O zaman onu feedback'te kullanmamız mümkün. Şurası referans input'u gene. Ondan sonra bu gene aynı feedback structure, araya bir observer koyarak yapıyoruz. Any questions here? Okay. So now let us try to understand what do we need for placing the closed loop poles at the required positions. Okay. So here I will actually write the following: x dot is equal to ax plus bu, y is equal to cx. This is my state space system. And how do I find the open loop poles? This is my open loop system. Okay? So how do I find the poles of the open loop system? What are they? G of s, this is G open loop of s, is given as c times si minus a inverse times b. This is my open loop transfer function. And we know that this is c times adjugate of si minus a, b divided by determinant of si minus a. Okay? So what can you say? And the poles are the s values which would make the denominator 0. Okay? But we know that they are the eigenvalues of A. This is the characteristic polynomial of the A matrix. That is dA of S. Okay? It is determinant of Si minus A. And we know that the poles are going to be the roots of this equation. So the open loop poles are the eigenvalues of the matrix A. Okay? So now let us try to calculate the closed loop transfer function of the system. Here we see what the input of the system is. The input of the system we selected as, in our closed loop, we select the input of the system as the reference input minus, I have the k vector times x. This is the closed loop system input rule in my state feedback architecture. And then I substitute this input into my open loop system. And then I'm going to obtain a closed loop state space representation. Okay? X dot is equal to a x plus b. Instead of u, I write r minus kx. R is the input of the closed loop system. So here I can actually think that this is my now closed loop system. Okay? This is the open loop. And by state feedback, I close the loop, and the closed loop system takes the reference input r, and it gives me the output y. Okay? If I write the right hand side here, it is ax plus br minus bkx here. I can collect x-related terms together, a minus bk, and I have x times x plus br. Okay? This is the state space representation of the closed loop system now. Okay? So here, R is my new input, closed loop input, and here Y is my closed loop output, and then this means that this thing is my closed loop state space representation. Okay? So here, if I give some names here to those matrices. If I write this as x dot is equal to a closed loop x plus b closed loop r, y is equal to c closed loop x here. These matrices would be the following. The closed loop A matrix is going to be a minus bk. Okay? Closed loop B vector is equal to the open loop B vector. And the closed loop C matrix, C closed loop is going to be equal to the open loop C vector. Okay? So we see that what this state feedback does is that it is modifying the A matrix at the end. Okay? So here, this is A matrix is a matrix, and B vector is a vertical vector, and the C vector is a horizontal vector. Okay? And we see that this multiplication is modifying. This is going to give me a matrix, square matrix with the same size as A. This multiplication is modifying the A vector of the open loop system. So now if I would like to adjust the closed loop poles of the system, if I would like to adjust the closed loop poles of the system, what should I adjust? I need to adjust the eigenvalues of the closed loop A matrix to be at the desired locations by choosing this K vector. By choosing this K vector, we are going to change the eigenvalues of the A matrix from the open loop poles into the desired closed loop pole locations. So what we are going to do at the end is that I will try to select this closed loop eigenvalues of the closed loop A matrix at the desired locations, which is going to complete our design process for this. Let us give a break. 40'ta tekrar başlayabiliriz.